A complex AI model from nothing. Meet Madison. She's a great person because she wants to help people. That's why she's an Asurian expert. You see, Asurian has many types of experts providing technical support for the customers. The experts come to people's homes, they work in stores, they give phone support, and they give messaging support. Madison works on the messaging support team by chatting and messaging with her customers. Now, she enjoys what she does, but she has a tough job doing it. That's because she has to retype a lot of messages every day, every single day, and it's a huge drain. And this is not efficient for her. Or in corporate speech, this is a pain point. Here's an example of a message she has to type very often. Wouldn't you get tired of typing this message every day, again and again? And here's another message that she keeps on having to retype. Now, this is not just Madison. In truth, we're dealing with a problem of a much larger scale. You see, we have hundreds of experts, just like Madison, who need to respond to tens of thousands of sessions every single day. Hi, I'm Matityahu Sarafsada, and come and see how we used AI to make Madison's life easier. I'm going to share with you our journey with the stumbling blocks met upon the way, while building for Madison a system to help her avoid retyping the same messages. We'll talk about the challenges faced during the data collection phase and during the modeling phase as well. But finally, we'll see the solution which helped us reach our goal, reaching a high accuracy model with the little amount of data that we had available. But first, a little bit about myself. I was born and raised in Houston, Texas. I moved to Israel in 2010, and I've been working in AI since 2015. A year later, I've earned my bachelor's degree in telecommunications systems engineering from Jerusalem College of Technology, Mechon Lev. I've also been working as a data scientist by Saluto since 2019, and in 2021, I became the data scientist team lead. My job at Saluto by Asurian is to make Madison's life easier. So one of the gifts that our team gave her was the canned messages feature, a prepared list of frequently used messages where Madison can simply scroll through, select, and send a message to the customer, thereby saving her much time from retyping the frequent messages that she usually sends. But we still had a problem because now Madison's canned message library grew very, very large. Because in addition to the default list that we gave her, she has her own list of customized and personalized canned messages that she added herself. So now it takes Madison even longer to search for the desired message. So we decided to use AI to automate and auto-suggest the canned messages, thereby saving Madison much time instead of searching for the appropriate message. And for the first iteration, the focus on the project was predicting the permission to troubleshoot canned message. Why this specific message? It was a business and a product decision. It gives assurance to the customer that the problem will be properly investigated. It also creates a unified language amongst the experts. Some examples of the message are, can I ask you some troubleshooting questions? Or I need to ask you a few questions to understand your issue. Will that be okay? The data collection, creating something from nothing. You see, ideally, the way I would like to prepare a data set is to collect many chat sessions and all the messages that were sent. Some sessions which use the default permission to troubleshoot canned message, and some which didn't. Then run a model on it, and done. Everyone lives happily ever after. However, we found very few sessions which used the default permission to troubleshoot canned message, because many sessions weren't troubleshooting related, and those which were, not necessarily did the expert prompt this permission to troubleshoot canned message. And even then, many times the experts use their own customized version of the message. So we introduced some NLP fuzziness to help us label more data for our data set. Fuzziness in NLP is the technique of finding strings that match a pattern approximately rather than exactly, such as the word apple and misspellings of it. A-P-P-L-E is the word. So A-P-L-E, A-P-P-L, and obviously apples would all be grouped together and fuzzy match as the word apple. So we use this technique and we devised the fuzzy match hybrid algorithm consisting of regular expressions, perfect match, the edit distance, and manual handpicking. The edit distance is a method which measures the amount of changes needed to get from one word to the next. Now, with this combined algorithm, we're able to find messages that match a pattern approximately rather than exactly. And through this method, we were able to collect more messages, but still did not yield enough data to train a model. So we use the power of semi-supervised learning. Semi-supervised learning is a method where we combine a small amount of labeled data with a large amount of unlabeled data during the training, helping us deal with our problem of a small amount of labeled data. Further, research has indicated that semi-supervised learning can give considerable results with less the amount of labeled data compared to a fully supervised learning project. And we devised our semi-supervised algorithm. First, we started with the pool of permission to troubleshoot CAN messages. That was our cold start, that small default list that we spoke about. Then we calculated the fuzzy match with that pool and all other messages, the potential messages to add to the pool. And if it matches the match threshold, it was added to the list. Then, at least when it was scalable, we reviewed, verified, and removed anything incorrect. And finally, rinse and repeat. We went back and did it again, running this process again and again each iteration, thereby growing the pool in each and every run. And it got more interesting as it evolved. At first, due to the limited amount of data that we had available, we started with a weaker base model, the fuzzy match hybrid algorithm, where the output of this model was used to be the generated label for the sample. However, once we were able to obtain enough data, we were able to train a more complex model, such as machine learning models, bag of words, TF-IDF, LSI, using boosting, using SVMs, and everything else. And finally, once we got even more data, we're able to start using deep learning models, LSTMs, transformers, and encoders. However, these are only self-labels, labels which are generated by the output of an algorithm. You see, in semi-supervised learning, we also need gold labels. Gold labels are those high-quality gold labeled data tagged by human beings, but we don't have, right? That's how we got into this problem in the first place. So we created a session tagger program to generate synthetic data. How? By manually injecting our desired target message into sessions which didn't have the message, but could have benefited from it if it did. And the results, from the synthetic data generation, we collected a few hundred labels. To remind you, these are those high quality hand labeled data, the gold labels. And from the fuzzy algorithms, we collected about 1,000 labels. Labels, again, which are set based on the output of an algorithm, the soft labels. And with this, we move on to our modeling process, urging our nothing to learn something. A little bit about our model's features. We use the speaker, which is the customer or the expert, as a feature, in addition to the message placement in the session. The message text encoded with Google's universal sentence encoder, and we use the length of a message. Now, this was done for that message and 10 previous messages leading up to that message for every message in our data set. So we were resulted with a 3-dimensional feature vector, n amount of features, x amount of samples, and then L amount of lags or previous messages leading up to this message, a time series based problem. We then split our time series session data into blocking windows, with our label of our model being, is the next message the permission to troubleshoot CAN message that I want to predict. Naturally, this left us with a huge label imbalance, as this message was used at most only once per session, out of the many messages a session can have, 50, 60. This left us with a class ratio of 98 to 2%. And as we probably predicted, the model could not converge. So we had to re-engineer the data set by undersampling in order to increase the amount of representation by the ones class in our data set, moving from a target label ratio of 98 to 2% to 89 to 11% ratio. And then the model began to converge. This was due to the proper label proportion. You see, the imbalance was high enough to resemble the reality, but it was low enough for the model to converge. So we started heading in the right direction, but we still were not optimized according to the business problem. This was because the model's loss function did not take into account our label imbalance. And therefore, the loss was mostly learning from the zeros class, that 89% representation in the data set. But the ones class is also important to learn from. And I could argue, maybe even more important, but we just did not have enough of them in the data set. To answer this problem, we introduced the binary focal loss to help the model better learn from that lesser label. More on that shortly. In addition, we used the F1/2 score instead of the MCC as a validation metric. This is because on a product level, on a business level, precision is slightly more important than recall. You see, at a product level, we prefer the customer's experience, the precision, rather than the conversion of the session, the recall. So this was to hold the retention and the happiness of our users. So we didn't only just use precision and not just recall, because the others are important as well. But if precision is a little bit more important than recall, so we used F1/2 score to give a slighter weight to that precision than to the recall in our validation metric. Now, what is the focal loss? Imagine you're at a soccer game, Barcelona versus Madrid, in a stadium packed with hundreds of thousands of fans coming to watch the game. Then, while watching the game, there goes Messi and scores a goal. Goal! 70,000 fans in the stadium are chanting goal! Now, at home, everyone watching the game is able to hear those 3 TV reporters in the stadium of 70,000 fans. But how could they hear them? They're in a stadium of 70,000 fans. They are strongly drowning out those 3 TV reporters who are also present at the game. How can those at home hear them? Because the sound room amplified the noise of those 3 reporters and decreased the noise of the 70,000 fans. Yes, the sound room has implemented a binary focal loss, giving higher attention to what was important, those three TV reporters, even though they were less compared to those 70,000 fans. And the same here. The focal loss in our problem amplified the weights learned by the ones class and reduces the weights learned by the zeros class, letting the model better learn from that smaller class in that data set, that ones class. And the rest was history. The loss converged, the F1/2 increased, and with early stopping before the overfitting and optimizing the threshold using our PR curve, we received the final results of the model with the F1/2 micro of 85% and F1/2 macro of 64%. But further analyzing the model's results, we learned that many of our false positives in production, in reality, were acceptable if they actually happened in real life. And that was interesting. And we started analyzing that. And this was due to the high variance amongst the experts in the message sending habits. You see, sometimes an expert will take a long message and split it up into smaller messages and send them each one. Sometimes even a question mark as his own message. So, if the model predicted something a little bit earlier, it still would have been acceptable. In addition, most of those false positives that we analyzed were actually early predictions and not later predictions as well. Our next steps would be using a scoring method in our validation metric and maybe even our loss function to credit those false positives which are still acceptable. In addition, with the advance in technology, we'd like to try other models and encoders such as GPT, BERT, and other different new state-of-the-art encoders. And last, on the business level, would be to predict more types of canned messages. Now, next time Madison is on a messaging session, and she should use the permission to troubleshoot canned message, the model will suggest the message to Madison, making her job at Asurian, bringing people closer to the technical devices much easier. Thank you, everyone, for your time. I'm happy to connect. That's a QR to my LinkedIn. There's my email. Looking forward. Thank you.